Okay, welcome back everyone. So in the last lecture we saw the discrete Fourier transform is a way of taking a vector of data and mapping it into the Fourier transform domain, which is essentially tells me what the components, the frequency components are. If I was going to add up a bunch of sine waves of different frequencies, how much of each of those sine waves would I have to add up to reconstruct my original vector of data? And so now we're going to talk about the fast Fourier transform, which is a way of essentially computing this discrete Fourier transform, but much, much more quickly. Okay, so this is really, really important. Okay, so the DFT, the discrete Fourier transform, is what's called an order n squared operation. So we're going to say this is order n squared computation. And the reason that this is order n squared, what this means is that n is the size of our data. Okay, so if we have 1,000 data points, then n would be 1,000. And what order n squared means is that if our vector had 1,000 data points, then the DFT computation would take on the order of 1,000,000 multiplications on a computer. Okay, and if I had 10 data points, then the DFT would take about 100 multiplications on a computer. Okay, so this is how this algorithm scales with the size of the problem. If I have a bigger problem, it takes more computation as that size of the data squared. Okay, that's what this order n squared means. And the reason is because this is really, we're taking a matrix, this DFT matrix, times a vector, okay, times our data vector. And if you recall, if I take a matrix times a vector, and this vector has n elements, and so this is an n by n matrix, then to multiply a matrix by a vector is an order n squared computation. So as I make the size of the system larger, the computation gets more and more and more expensive that way. Okay, good. So what I'm going to tell you about now is the fast Fourier transform. So the fast Fourier transform. This is the FFT. Okay, the fast Fourier transform returns, essentially it does the same thing that a discrete Fourier transform does. It takes your data f and it returns this f hat, this set of frequency components. So you could get power spectra and things like that, and you could use it for filtering. But it does it in a much, much, much faster way. So it goes from order n squared down to order n times log of n. Okay? And so we'll figure out what this means in a minute in terms of practicality. But the fact that we can go from an order n squared computation to an order n log n computation is a huge speed up. So this is much faster, especially for large problems. Okay? Which is really good. So for example, this is really one of the most important algorithms ever developed. It has dramatically changed the world that we live in. Okay, so every time you use your phone to make a call, or you send a picture to a friend over the internet, or you stream a movie to your computer or your TV, you're taking advantage of this fast Fourier transform. This order n log n computation is what makes all of that possible. It makes satellite communications possible. It makes image compression, real-time audio and image compression possible. And without this fast Fourier transform, if we had to do everything in order n squared time, we wouldn't have lots of the cool communications technology that we have today. So this is really, really important stuff, very interesting. And I'll give you an example that compares the two of these algorithms a little bit more detail. But I just want to give you a little bit of history. So this was developed by Cooley and Tukey, that's Tukey, in 1965. And this was a collaboration between IBM and Princeton. Okay, so IBM Labs and Princeton University, Cooley and Tukey in 1965 developed this fast Fourier transform algorithm. They recognized that the DFT was super powerful and useful, but it was too slow. And so they came up with this fast algorithm that had better computational scaling, and they changed the world. Okay? What's interesting, what's really fascinating to me, is that this fast Fourier transform was technically discovered over 150 years earlier by Gauss, by Carl Friedrich Gauss. So this was actually discovered by Gauss in 1805. This is absolutely remarkable. So Gauss, being the genius that he was, did all kinds of numerical math in his head to predict the motion of planets and all kinds of other interesting mathematical modeling. He was a human walking computer. And he realized that he was doing a lot of these computations, these DFT type computations that were order n squared. And he was doing them in his head, so he wanted a faster way of computing the trajectories of planets. And in his notes, he just scratched out a fast Fourier transform algorithm in full generality. But it went relatively unnoticed and undiscovered and kind of wasn't an important algorithm because at the time of Gauss's genius, he was the walking computer. You couldn't implement this on every, there weren't computers in the world. There weren't cell phones. There weren't satellites. And so this algorithm never really took off until Cooley and Tukey rediscovered it in 1965. But I think this is just an interesting note that sometimes, really powerful, fascinating things have been discovered way before they found a use, or at least a broad use. Okay? Good. So I want to give you this little example that just illustrates why order n squared is so much worse than order n log n, and why this was such an important algorithm for the world. Okay? So I like to think about this in terms of how long would it take to compress a couple of seconds of audio, right? Because that's something we all do. We stream music from the internet, or we listen to an MP3 on our phones or computers. And all of this information has been compressed using a discrete Fourier transform, or a fast discrete Fourier transform. And so I just want to convince you that if we were stuck doing these slow discrete Fourier transforms and we didn't have FFTs, then we wouldn't be able to have streaming music or pictures or movies or any of the things that we've come to find so kind of standard and useful in our day-to-day lives. Okay, so let's just write this down. We have this order n squared computation, and we have this order n times log of n computation. Good. And so the example that we're going to do, we're going to look at an audio signal. So audio is sampled at 44.1 kilohertz, which means that for every second of audio, you have 44,100 samples per second. Okay, that's a lot of samples of audio. And that means if I had 1 second, I would have 44,000 data points in my vector of data. If I had 10 seconds, I would have 440,000 sample points. So let's look at that case. So we have 10 seconds of audio. Okay, and so our data vector f, f is our data vector. This is essentially the sound file that you're using to play this 10 seconds of audio. This has something like 441,000 numbers, elements. Okay, so this is a huge 441,000 tall vector. That means that n equals 441,000. Okay, so let's say that we have this 10 seconds of audio, and I want to compress it so that I can send it on the internet, or decode an MP3 that has this many elements. So in the case of a DFT, I would take this number squared, and that's how many times my computer would have to multiply two numbers or divide two numbers. So it's order n squared, which is about 2 billion multiplications Okay, that's actually still pretty expensive, right? Like my phone might have a little bit of trouble doing 2 billion multiplications really, really quickly. Whereas for the fast Fourier transform, because this is an order log n, log of this number is about, 1, 2, 3, 4, 5. So log of this n is about 5. So this is on the order of 5 times n. And this is only about 1/4 of a million multiplications. Volts, okay? And so this is a huge, huge, huge difference, right? We have something like an 8,000 times speed up. And this is just for compressing 10 seconds of audio, or fast, Fourier transforming 10 seconds of audio. If I had to do the DFT, the discrete Fourier transform, this big matrix, it would be extremely expensive. But now that we have the fast Fourier transform, we can do this 8,000 times faster for this 10-second clip of audio. Okay, so cell phones, iPods, satellite TV, all of this wouldn't work without the fast Fourier transform because it would be too expensive to code and decode the signals. Okay, so in the next few segments, I'm going to show you how we use the fast Fourier transform to compress and decompress images and audios and code signals. But I just wanted to give you this kind of high-level sketch of what it really means, why the fast algorithm, this n log n, is so important. It literally means your computer is doing less work for the same fast discrete Fourier transform. Okay? All right, so next time we'll talk about compression and audio signals and all kinds of cool stuff that you can do now that we have a fast, cheap Fourier transform. Okay, thank you.